I'm very pleased to introduce my friend Chris Hill, Christopher T. Hill. Wikipedia says the following. It's a Russian version. It also says that Chris Hill is a theoretical physicist. There are three kinds of theoretical physicists, one kind that knows how to count and one kind that doesn't. Thank you very much. He did his undergraduate work in physics at MIT, where he got his bachelor's and master's degree, and his graduate work at Caltech, MIT, Caltech, fly-by-night organizations. His research sponsor was Murray Gell-Mann, a famous theoretical physicist. He has made many contributions to the subject of electroweak symmetry breaking. In the newspapers, they call this the Higgs phenomenon, or the Higgs particle, or the Higgs thing, and you might have run across that. Oh, then there's a line here that's really good. He is the originator of quasi-infrared, fixed point, top color, top quark, condensate, top seesaw models, and dimensional deconstruction. Said it in one breath. He's also an originator of cosmological models of dark energy and dark matter based on ultra-low mass bosons associated with neutrinos. He is a fellow of the American Physical Society and currently the chairman of the Theoretical Physics Department at Fermilab. He's been noted particularly for his close contact with the experimental groups at Fermilab, and his work today touches on many aspects of the field of particle physics, accelerators, non-accelerators, and astrophysics. So with great pleasure, I introduce Chris Hill, whose topic will be Symmetry and the Origins of Mass.
Well, it's a great pleasure to be here. I think I was here maybe 10 years ago or something, smaller group, and I don't think you had this program then, or I wasn't part of it then. But it's a delight to be here today to talk about a subject dear to my heart. So in 5 years, the written laws of physics are going to be different than they are now. And that's saying a lot because I'm talking about the fundamental laws, the fundamental description of nature. And at the moment, we may have written the right equations, but we don't know. And probably we haven't. Probably there's going to be a surprise or two. And so that's a very exciting passage for the science of physics to go through from, sort of like, think of pre-Newtonian law of gravitation, the era afterward, when you finally knew that law and all the wonderful things you could do with it. We're going to have a similar experience in the next few years, both from things we've built at the Tevatron and operated, and maybe we'll see some final hint of something remarkable, but certainly the Large Hadron Collider that's about to turn on when it's repaired in a year at CERN. What will happen, I believe, is that the so-called energy frontier, by energy frontier, we're actually looking at the distance frontier, the shortest distances. We will have some new organizing principle of nature revealed to us, something that applies everywhere throughout the universe, that describes everything, everywhere, and it will, lead us to the next set of questions that are unanswered and focus our understanding in a way that we can't really anticipate right now. In order to think about something like this, we invoke something that's tried and true. It's the concept of symmetry. And so we've already made up some candidate organizing principles, which I'll be telling you a little bit about. One is supersymmetry, then the idea that maybe there are extra dimensions of space that we haven't seen that are curled up and have the symmetries of space and time. Or maybe there are new strong interactions that are somehow associated perhaps with these two symmetries, but contain their own new set of rules, new symmetries, and control the things that we're going to hopefully see soon. It's also possible there's something unexpected. And so I always invoke the heretic. That's the famous Giordano Bruno, who back around 1600 was vehemently arguing that the sun is not the center of the universe. The earth is not the center of the universe. The sun does not go around the earth. The earth goes around the sun. And moreover, the sun is not the center of the universe. It's part of a large galaxy, he called it, and that these galaxies are not the center of the universe, that there are many galaxies, and that there might be intelligent life in these other galaxies. And Bruno Giordano was burned at the stake. And that made life a little complicated for people like Galileo and others who had to sort of tone it down a bit. So all theoretical candidate organizing principles in our modern view of things involve hypothetical new symmetries. And symmetry, we have learned in the 20th century, because it's really a 20th century revelation, is truly fundamental to our understanding of the basic laws of physics. It's indispensable. And once you figure out the correct symmetry, you usually can figure out very quickly what the associated equations and what different things are doing to describe phenomena. The thing that's bizarre about mass is that mass is always associated with a breaking of symmetry. Because if you take the masses of things and you set them to 0, like the electron mass, the electron becomes a simpler object. It falls up into two pieces, something we call a right-handed electron and a left-handed electron, and these particles are independent of one another. They're like a pair of neutrinos. This right-handed thing never turns into a left-handed thing. The left-handed thing never turns into a right-handed thing. But when the electron has mass, these two things come together and they're blended. And left can flip into right, can flip back into left, flip back into right. In fact, that is the phenomenon of mass. Now we say there's more symmetry when we set the mass of the electron to 0 because I can take the left-handed thing and I can do all sorts of things to it and not mess with the right-handed thing. For example, typically, I can study the interactions of the left-handed particle in isolation, and it never involves the right-handed particle. I can just take, in quantum mechanics, we have this wave description. I can redefine the wave. I can consider a wave of one wavelength, and I can consider changing it to a different wavelength, but preserving its left-handedness. I can't do that when the electron has mass, because if I change the wavelength of an electron wave of a left-handed particle, I will change the right-handed wave as well. So the two things are locked together by mass. They become independent. There's more symmetry. There's more flexibility in what you can do to a left-handed or right-handed electron when the mass is set to 0. So the mass is breaking that symmetry, and it's uniting these two different things together to form the electron. Often easier to discover the underlying symmetries than to discover what causes them to be broken. And that's why today we're in a remarkable situation. We understand exactly how left-handed electrons differ from right-handed electrons. Left-handed electrons, and by the way, left-handed means if the electron's going that way, the electron is a little top. If it's going that way, if it's right-handed, you curl your thumb in the direction of the momentum, and that determines how the thing is spinning. If it's left-handed, you curl like this, and it's spinning this way. So it's spinning in the opposite way if it's left-handed compared to right-handed. So there are different, we call them chiralities of the electron. We know how the left-handed electron is different than the right-handed electron. The left-handed electron participates in certain interactions that the right-handed does not. We understand those interactions remarkably well. We understand all of the equations that describe them. But we don't know what unites the left and the right to make the full electron. Stunning, but we still don't understand the breaking of the symmetry, but we understand what would happen if we set the mass of the electron to 0. So I'll show you a little in a cartoon what I just told you in words a little later. The concept of applying symmetry was a 20th century revelation. And it really began, I think the deepest statement that connects symmetry to physics is something called Noether's theorem. And Noether's theorem was proven by the greatest female mathematician who ever lived and one of the top 5 or 6 mathematicians who ever lived, Emmy Noether. Her life story is quite interesting and very tragic, and I don't have the time to go into it. I will recommend a book to you, however, that has a great chapter on her biography, and you should read it. She proved her theorem shortly after arriving at the center of physics in Europe in the early 20th century, Göttingen, Germany. And in Göttingen, she worked as a low-level kind of a researcher, never able to get through the glass ceiling, being promoted to professor. But with the help of some friends, eventually, the man who's recorded the title of greatest mathematician of the earliest 20th century, and this guy, they managed to convince the faculty of Göttingen to do something absolutely astonishing. Promote Emmy Noether to the rank of professor. And this was about 1931, if my memory serves, something like that. The following year, she was fired, as were all minorities in the German academic system by the Prussian Academy, and I won't tell you the rest of the history. Fortunately, she came over to the States, where she was a professor at Bryn Mawr University and simultaneously at Princeton, but tragically died a few years later of cancer. So I'm going to tell you what her theorem is and tell you a little bit about how it controls nature. But I want to begin by telling you what symmetry is, because it's a theorem that connects symmetry to physics in a fundamental way. So what is symmetry? Well, you all know it when you see it. And it's incorporated into all sorts of things like architecture, music. We see it in physiology. We see it throughout nature. And we see it at the fundamental level of the laws of physics. So the architect of this famous structure has incorporated symmetry. And all you have to do is take a picture of the Taj Mahal and then go to Adobe Photoshop and reflect it. What I mean is you map every point to the left of some imaginary axis into an equivalent point on the right and vice versa. And notice what happens is the image stays the same. The object is unchanged under this operation of swapping left and right. In this particular case, this is the simplest symmetry, just swapping points on the left and points on the right. In fact, I think this picture makes it into the book I'm going to recommend for you. And I think I took this picture, and it was a slightly cloudy day. Nice thing about using pictures in books that you took is you don't have to get permission, which is a real pain when you write a book. And you can notice that the clouds, of course, change their positions. They don't respect the symmetry, but the structure does. And this is the simplest possible reflection about an axis, symmetry that many objects have. And the architect is in some sense appealing to something divine, something fundamental in nature by incorporating it into the design of the Taj Mahal. We can take the next step to something that is a little less trivial. It's the sort of simplest, non-trivial example. We can look at the symmetry of an object like an equilateral triangle. Right? This is an equilateral triangle. Sides are all the same. Angles are all the same. And I put some labels on the vertices, and I've labeled the so-called symmetry axes. And with the Taj Mahal, we had one symmetry operation, just flipping, reflecting through the axis in the middle. Here we have a number of symmetry operations. The things we can do to the triangle, lifting it up, bringing it back down on top of itself to preserve the appearance. So these axes and these labels, forget those. Just think of a pure triangle. How many distinguishable operations are there that allow you to pick the triangle up and put it back down on top of itself? And I don't have the time to go through this in detail, but here's the list. You could do nothing. That's a symmetry operation. Everything in nature has the do nothing symmetry operation. Or you could rotate the triangle by 120 degrees. If I rotate it by 120 degrees, A comes here where B is, B goes here where C is, C goes up here, so we end up with CAB for the positions of the vertices. Or you could rotate through 240, or you can reflect about the various axes. So I can do exactly what I did to the Taj Mahal. I can reflect about axis 1. That will swap C and B, leaving A where it is. So you see then you get ACB. But you can also reflect about 2 additional axes. So now you see the symmetries of the equilateral triangle are a little more subtle. There are about 6 of them. There are exactly 6 of them, 6 operations. You could fuss about whether you could rotate through 360 degrees. But rotating through 360 degrees is the same as doing nothing. And if you want to distinguish between rotating through 360 and doing nothing, you're not focused on the triangle. You're really focused more on the path that you took as you pick the triangle up and bring it back down. We don't care about the path that we take. We just care about what happens, what takes the triangle from one position to another. And doing nothing is therefore equivalent to a rotation through 360. So if you think along those lines, you'll be led to these 6 symmetry operations. You might even say, well, it had to be 6 because I had 3 vertices, and it has to be the number of permutations of 3 vertices, and the number of permutations of 3 objects is 3 factorial, which is 6. You might think that. But if you go to the next more complicated thing, which is the square, that argument would predict 4 factorial symmetry operations, which is 24, and that happens to be wrong. So your homework is to go home and make a list of the number of symmetry operations of a square, and you should get 8. Okay? So that raises an interesting question. How do you know in principle if you're finished? How do you know your list is complete? And answering that question leads to something really, really profound. What if we think of these 6 things as numbers? What if we try to figure out how to multiply these numbers together? So for example, I could do a rotation through 120, and then I could follow it by a rotation through 240. And that would get me back to do nothing. So already I can see there's kind of an algebra here. R120 times R240 equals do nothing. What happens if I make a complete list of all of these multiplications I could do? Well, this is what you get. This is the multiplication table of what is called the symmetry group of the equilateral triangle, the collection of all the symmetry operations. So if I start with A, is in blue, so I could do my rotation through 120, follow it by B, which is in green, let's say rotate through 240, A times B gives me back 1. But it's more complicated than that. In fact, I could start with a reflection about axis 1, follow it by a rotation through 240, and notice I get a reflection about 3. So you have to work all of this out, and you can do it. And I suggest very strongly that once you've found the 8 symmetry operations of the square, you work out the 8 by 8 multiplication table. Now this kind of multiplication is really amazing. It's not like normal multiplication. Normal multiplication, 3 times 4, is commutative. That means 3 times 4 is equal to 4 times 3. But symmetry group multiplication is generally not commutative. We just calculated R1 times R240, we got R3. What if we do them in reverse order? Let's do a rotation through 240 degrees, followed by R1, we get R2. So A times B is generally not equal to B times A. Does that mean this is irrelevant to the physical world? Well, in fact, it's quite relevant. Here's a book. Actually, does somebody have a book? Anybody got a book they could loan me real quick? Got a book? Good. Here's a book. So I'm going to hold the book, binding down the way I would open it, on a desk. I'm going to take the x-axis and the y-axis. I'm going to rotate right-hand rule 90 degrees about x, followed by 90 degrees about y. See how it ends up? Here's the title here. I'm going to hit the reset button. 90 degrees about y, followed by 90 degrees about x. Quite a different position. A times B, B times A. Our world is not commutative. So the simple mathematics that was developed long ago to count sheep and make banking systems work when they work, is not sufficiently general to describe nature. And we need something that goes further. And you can see it here. But groups are amazing. Symmetry groups all are magic squares. Notice that every element of the group, all of the 6 elements, occurs once and only once in every row. And it occurs once and only once in every column. That's a theorem. All symmetry groups are magic squares. And all symmetry groups contain subgroups. So for example, if I forgot about the reflections, for example, suppose I'm just a two-dimensional being and I live in the plane, and I don't know there's a third dimension. And I sort of never think about lifting the triangle up and flipping it and bringing it back down, which is what a reflection is. Then the only thing I'd ever talk about would be the rotations. And the rotations by themselves form a 3 by 3 magic square, and that is a rotation subgroup. Those are called the internal operations, the things you do living in the world, the two-dimensional plane, whereas the reflections are external. The group knows there's a difference between reflections and rotations, because if I do a rotation followed by rotation, I always get back a rotation. But if I do a reflection followed by a rotation, I always get a reflection. If I do a rotation followed by a reflection, I always get a reflection. And if I do a reflection times reflection, I'm always back in the plane. I get a rotation. There's a difference we call parity. The reflections have odd parity. They're like the number -1, whereas the rotations have even parity. They're like the number 1. And so that's 1 times 1 gives you back 1. -1 times 1 gives you a -1. 1 times -1 gives you -1. And -1 times -1 gives you back 1. So these are common features shared by all the symmetries. So the mathematicians realized that there's a much better way of talking about this than drawing pictures and flipping them around. They made a bunch of rules. And they said, what is a symmetry group? It's a collection of elements which are the symmetry operations, the 6 things I could do to the triangle. It has a multiplication operation. You can multiply 2 of them together, and it must close. You must get back a member of the set. See, that's how you know that you've got them all. Because if you do A times B and you get something that wasn't on the list, then you know that you got to add that thing to the list. Yes, sir? Oh, I'm sorry. That should be R sub Z or whatever you want to call it. Yeah, I'm sorry. That's a typo, and you may see a few more. Good. Thank you. There's the do-nothing operation, which is just like multiplying by 1. If I do nothing and follow it by x, I always get x. And here's a really interesting piece of fine print. If you multiply by 1 on the left, you get the thing back. And if you multiply by 1 on the right, you get the thing back. Remember, it's not commutative, so we have to specify that 1 acting on the left is the same as 1 acting on the right. If you gave that up, you wouldn't have a symmetry group. You'd have some other fancy thing like a ring or a module or a field, some other thing that mathematicians have invented, but you wouldn't have a group. Each element has a unique inverse, and the inverse means that if you multiply RK by its inverse, you get back 1. And the inverse acting on the left is also the inverse acting on the right. Sometimes certain mathematical systems don't have that property. There are left inverses and right inverses. For example, non-square matrices have different left and right inverses. But for symmetry groups, it's left or right. You can multiply by the inverse and you get back 1. And this is really important, and I don't have time to go into it, but the multiplication is associative. So A times bracket B times C equals bracket A times B times C. And that's really tricky, but it's true of all symmetries, and we physicists have never found a use for non-associative mathematics that was any good. We tried, but we couldn't find it. Now, you know, it's really astonishing that you can distill these rules by playing around and sort of capture the essence of symmetry. But what's even more astonishing is once you've done it, you can now discover all possible symmetries just by asking what are all possible collections of elements that satisfy those rules. Now, I showed you the simplest, which was a discrete triangle, and I showed you the even simpler Taj Mahal. But these rules apply to anything. For example, if a bottle without the label on it, I can rotate that about the axis, the z-axis. The difference here is that this is a continuous symmetry. There's no smallest rotation. with the flipping of the triangle, you got to take steps. You know, there's no fraction of a rotation that you can't rotate through 12 degrees. You won't bring it back on top of itself. You can't reflect half through the symmetry axis. I don't know what that would be. So you have to take definite steps. Whereas with this thing, it's continuous. And it turns out, using these rules and the fact that continuous things allow you to use a very powerful mathematical tool called calculus, mathematicians very early in the 20th century were able to list all possible continuous symmetries. And they are basically generalizations of spheres, or circles for that matter. Here they are, the spheres in n dimensions. So the symmetry of this bottle is actually O2. O2 is, if you look down from above, you're just seeing a circle and you're rotating a circle. The rotations of a circle define the symmetry group O2. If it's a basketball fixed in space, you can rotate about an x-axis, a y-axis, a z-axis. That's called O3. And you can go to any number of dimensions. You can go to 156 dimensions and have a basketball in 156 dimensions, and you can rotate it. That would be SO or O 156. Whether you put the S there or the O is just a question of whether you allow what's called an inversion. You can take the ball and you can map any point here to this antipodal point through the center. And if you include that as a symmetry operation, it's O. But if you don't, if you throw that out, it's called SO. Then you can say, what if the coordinates of my dimension are complex numbers? Now you have what are called SU groups. And why would SU groups be interesting? Because quantum mechanics is always defined in spaces with complex coordinates. So when I talk about quarks, a quark can come in 3 colors. This is a whimsical thing we say, that quarks have colors. What we really mean is quark is a vector in a 3-dimensional space whose coordinates are complex numbers. And you can rotate the quark in that space, and that is a symmetry. And that symmetry is SU3. And once I say that, I can quickly figure out what the forces between quarks have to be, and I can figure out what holds them together inside the proton. Do you have a question? Oh, no. Okay. And then there are some other funny groups. And these things have really play a major role in string theory and so forth. But I'm just showing you this as a mathematically interesting point, that how you can quickly get, by taking a geometrical problem, turning it into algebra, and then solve it. That's what happened here. Now the discrete groups are much harder because you can't use calculus, and classifying all of them required computers. And it wasn't solved until the 1980s. There's a wonderful article in the 1980s by a fellow named Gorenstein called the enormous theorem. It's one of these mathematical proofs that no human understands. Humans understand parts of it, but the computer was instructed to search, and it produced a list of all the discrete groups. So what does this have to do with nature? So in nature, we see a bunch of symmetries. For example, the laws of physics don't depend on where you are in space. Now you can see that pretty easily. You know, I put the bottle here, and it's got a certain temperature and certain chemical composition. I move it over here. It's not boiling. It didn't change blue. It's the same water, same temperature. The laws of physics governing that bottle, whether it's there or there, are the same. And you could take the bottle off into, in a spaceship and go to some distant galaxy. The water will stay the same. And we have lots and lots of experimental evidence to support that. Furthermore, this water has stayed more or less the same over the past hour. In fact, it'll be the same tomorrow if I don't drink it. Water isn't changing in time. So there's a symmetry, meaning it's invariant. The bottle's the same. The water's the same if I translate in space. And I can translate in any of 3 directions, back this way, or up and down. And in time, thing is moving in time. It's not changing. That is a symmetry. The laws of physics that govern this system are not changing in time. I can rotate the bottle. I can rotate it about any axis. the laws of physics are the same. The water doesn't change its properties. I can actually boost the bottle, make it move uniformly through space. Same water, same laws of physics. You're moving right now. It's a question of what you want to say you're moving relative to. You're not moving relative to her, and she's not moving relative to you. But compared to Martians, you're moving quite fast around the sun. Compared to people in Alpha Centauri, moving even faster relative to them. Compared to people in Andromeda, even faster. So we are moving, but we don't sense it, because the laws of physics don't change when we move. Those are all symmetries of nature. And they're all discussed in this book. So here's the commercial. Now we'll move on. So what did Emmy Noether prove? She proved a theorem in mathematics that is as important as the Pythagorean theorem. The Pythagorean theorem is quite possibly the most important theorem in mathematics until Noether's theorem comes along. Noether's theorem defines how physics works. And it's profound how deeply it penetrates into physics. What she proved was that for every symmetry of the laws of physics, and these are continuous symmetries now, moving the bottle is a continuous symmetry. I don't have to take a small step, a smallest step. I can move the thing a nanometer if I could do it, and the laws of physics don't change. That's a continuous symmetry. For every continuous symmetry, there's a corresponding conservation law. Conservation laws all correspond to continuous symmetries. There's a one-to-one correspondence. So what are they? Well, for the 3 spatial degrees of freedom of the bottle, laws of physics don't change if you move in x, y, or z. There's momentum conservation. The fact that the laws of physics don't change by moving to a different point in space means there's something called momentum that is conserved in every physical process. The total momentum before some interaction occurs equals the total momentum afterwards. And notice that 3 ways you can translate leads to 3 components of momentum. Momentum is a vector. It points in a direction. Because the laws of physics don't change in time, Noether's theorem, there has to be a conserved quantity. That thing is called energy. And vice versa, energy is conserved. The total energy before a reaction equals the total energy afterwards. And you have to be a really good experimentalist like Leon to keep track of all the ways energy can leak out of something, or momentum for that matter. But it's true. The energy is conserved. And running that backward, there must be a continuous symmetry, and that corresponds to motion in time. The laws of physics do not change in time. Rotations correspond to angular momentum, and actually, here's the seeds of the Einstein theory of relativity. The fact that the laws of physics don't change under motion actually leads to a generalization of angular momentum, which is called relativistic angular momentum, in the sense that motion is a rotation in space and time. And in the Newtonian theory, where you can think of the speed of light as infinite, when you calculate this, you get 0. But in Einstein's theory, where you are allowed to talk about things going near the speed of light, you calculate these things blend together. Rotations in space and rotations in space-time are all collected together into 6 degrees of freedom. The rotations in space-time are motion. When I move, I'm rotating in space-time. And that leads to the 6-component angular momentum. How do we prove Noether's theorem? Well, there are many ways of proving it. The simplest way is to suppose it wasn't true. If it wasn't true, let's say on Tuesdays gravity was a little weaker than it is on Wednesdays. Then on Tuesdays you could pump water up into a water tower. And on Wednesdays, when gravity was strong again, you could drain the water out, and you'd get a net energy gain, which is the mass of water times the difference between little g, which is just the strength of gravity at the surface of the Earth, on Wednesday minus Tuesday, times the height of the water tower. You could build we'd solve the energy crisis immediately. We just build, instead of windmills, we'd be putting up water towers everywhere, pumping them up on Tuesdays and draining them on Wednesdays and getting that energy out. Energy would therefore be produced because the laws of physics were changing between Wednesday and Tuesday. But the laws of physics don't change. G Wednesday really equals G Tuesday, therefore you don't get any energy. Energy is conserved. In fact, you'll just lose energy from all the mechanical friction and whatnot. So this raises an interesting question. What's the symmetry that's associated with conservation of electric charge? Now this one is quite mysterious. About the time of Noether's theorem, people were getting a handle on it, but it took a long time. Ben Franklin, you know, invented the concept of electric charge, and the force between electric charges was a generalization of what Newton did for masses. It's really a profound step to invent this notion of electric charge. And, positives repel, and negatives repel each other, but positives attract negatives. And all of that was worked out by Franklin and I think Watson in Britain at the same time. But the electric charge in a system is always conserved. I have a picture. So if a bunch of electric charges flow into a little box, and I don't know if I have the cartoon, yes, then later the same number will come out, and if you don't get the same number out, then somebody's hiding in here. The total number afterward equals the total number before. That's electric charge conservation. Okay? You can't create or destroy net electric charge. Okay? That's a symmetry. Electric charge is conserved. So running Noether's theorem backward, every conservation law is associated with a continuous symmetry. What is the symmetry? And it's not actually until you get to quantum mechanics. This is rather astonishing. It's not until you get to quantum mechanics that you can really understand what that symmetry is. And here's what the symmetry is. Suppose I have an electron. The electron is just sitting there. It's moving in time, and it has a certain momentum and a certain energy. It's actually a wave. And let's suppose I just randomly change the momentum and energy of the outgoing electron. I change the wavelength and the frequency. So there's this wave coming in, and I change it. Change its frequency and its momentum. Well, I can't normally do that because that's changing its energy and momentum according to quantum mechanics. But in quantum mechanics, this is a wave. And I can add a spooky kind of a wave on top of the electron. So my outgoing electron, I can add another wave moving parallel to it. And I can compensate the change that I just made. So that the electron that I started with is indistinguishable from an electron of a different momentum and a certain wave moving along with it. So that the sum of the momentum of both of these and the energy is the same as I had here. You can't tell the difference in quantum mechanics. For those of you who know about complex numbers, this is just a complex function of space, and all I'm doing is I'm multiplying it by a phase factor, which is an arbitrary function of space, e to the I theta of x and t. Then I'm superimposing on top of it a particular type of wave, and that recovers the original electron state. It's kind of weird, but it's a symmetry that you could have. And it leads to electric charge conservation. This is what is the Noetherian connection between electric charge conservation and symmetry. But once we identify it, it immediately tells us something profound. What if we kick the electron here and separate off this mysterious thing that we added to preserve its identity? Well, now what has happened is the electron has radiated into space a particle. And that particle is called a photon. So by demanding this spooky identity symmetry of the electron, I've introduced something that immediately leads to a physical consequence. It leads to the existence of something called the photon. Now, this physical process actually can't happen. An electron by itself in free empty space cannot just change its state of motion and radiate a photon. That would not conserve energy and momentum. But this can happen. An electron can, for an instant, radiate a photon. The Heisenberg uncertainty principle allows a little variation in energy and momentum over a brief period of time and over a short distance in space. And that photon can be received by another electron. Remember, this thing is indistinguishable from something where that photon was just riding along. So in some sense, that photon is already there. The electron changes its state of motion and radiates that photon. Then this photon joins with this electron, making a new electron that you can't distinguish from an electron without a photon. That's the underlying symmetry. That is the electromagnetic force. If you calculate this in quantum mechanics, you get exactly the inverse square law Coulomb force. There's only one thing you have to put in. It's the strength or the square root of the probability, a fancy thing. We talked about this in one of the breakouts. The so-called quantum amplitude for this photon to be emitted, that's called the electric charge. So the point is, Noether's theorem, and you correctly identify the symmetry that leads to electric charge conservation. Noether's theorem guides you to the full theory of electrodynamics. And the symmetry principle is this blending together. And by the way, we now know, since about 1972, that every force in nature is a gauge force that involves this spooky type of symmetry. For example, quarks, as I said, come in 3 colors. And when a blue quark can be rotated into a red quark. But when you do that, you emit some color information. And that color information is carried by a spooky gauge field. And that is, in this case, a blue anti-red. The red going backward in time is called anti-red. This is going forward in time. A blue anti-red gluon, which can collide with a red quark, turning it into a blue quark. So this is precisely how quarks interact. And it's what holds the quarks together. Quarks make up protons and neutrons. And this force holds them together. All of these particles have been made in the lab and observed. The thing about quarks is when you observe them, you've got to look really close, because what happens is they briefly come out of the proton. They go quite a distance, many proton diameters. At Fermilab, about 100 proton diameters as free quarks. But then this force gets stronger and stronger. And it makes lots of particles and antiparticles and dresses these quarks up into color neutral states. But you get this beautiful collimated jet of particles that are the memory of that free outgoing quark. There's a lot to say about this. This force behaves much differently than this, even though it comes from the same principle. The force of electromagnetism dies off as you separate electrons. It goes like 1/r². The force between quarks is constant as you separate the quarks. And the reason is the glue actually has color. It's blue anti-red. You could also have blue anti-green. You could have red anti-blue. You have 8 different types of gluons. As you separate the quarks, the gluon field collapses into a tube. And it costs you energy in proportion to the distance you separate the quarks, and that gives a constant force. That's why we can't rip quarks out of the proton permanently. They always seize up and get pulled back into color-neutral particles. But we can see them, and they were first photographed in 1971-ish or something at the Stanford Linear Accelerator, where photons were shot inside the proton, and we could see the individual quarks dancing around. At that point, we also noticed there was some gluons floating around too. So all forces in nature are described by this principle. Even the weak force, but here we find yet something new. Now, an electron can convert to something called a neutrino and emit something called a W. The W can convert an up quark to a down quark. So now we're actually changing the character of the particles, what we call their flavor. And here, something new, the W particle is extremely heavy. And that makes this force have a very short range, and we call it the weak force. If we turned off the weak force right now, you wouldn't notice a difference. But if we'd turned it off 5, 6, 7 billion years ago, you wouldn't be here. Because it is necessary for the weak force in order to produce the heavy elements, in order to reseed clouds that can form stars and planets and lead to carbon-based life. Okay. So how does something get mass? I'm going to skip ahead a little bit here. I'm going to talk about how something like the W can get a mass. And as I said, the best way to think about that is to turn off the mass. See, if it has no mass, it's just traveling at the speed of light. This is time, this is space. This is how a particle travels if it is traveling at the speed of light. Its distance increases with time, and the ratio of the increase in distance to the increase in time is the speed of light. The problem is the W particle of the weak force is very heavy. How do we get a gauge field to be heavy? It turns out because of the symmetry, in order to do this, you have to somehow break the gauge symmetry. Now you have to fake the breaking of the gauge symmetry. You have to hide the gauge symmetry. If you don't hide it and actually break it, the quantum theory falls apart. So how do we do that? We fill the vacuum with something that the W boson can talk to. So it's something, the W has a charge called a weak charge. We fill the vacuum with something that has the weak charge. A W collides with this thing in the vacuum, and it actually eats up a bit of the thing in the vacuum. And then it collides again, and it gets rid of it and goes back to a W. And it's this blending of the gauge field with the vacuum condensate that has the charge that leads to a massive W, something that can sit still and just move forward in time or move at a speed less than the speed of light. If we hit the vacuum hard enough, we can excite this condensate and we can make a particle. That particle is called the Higgs boson. And that is what we are searching for because we know something like this has to exist. And today, we're getting rather close. We know that the Higgs boson is much heavier than the proton. This is roughly proton masses. Today, we know the Higgs boson is heavier than about 110, 115 proton masses. And actually, our theory predicts we should have already seen it to a high confidence level. We're getting kind of out here in the limbs of the probability distribution for finding the Higgs. That may be telling us that the theory of the Higgs is in trouble. We should have already seen it. At Fermilab, our experiments have already touched the prediction on the nose at a mass scale of about 170 proton masses. And soon we're going to be ruling out this entire range or finding the Higgs. This is what's so exciting. If the Higgs is lurking in this mass range, we will see it at Fermilab within the year. This is the projected probability of finding the Higgs in terms of its mass range. This is a particularly easy range because the decay properties of the Higgs are quite obvious. The Higgs decays here to muons, charged particles that are leptons, and there's virtually no background dirt in the experiment that would fake something like that. However, if the Higgs is much lighter, down in this range, it decays into B quarks, beauty quarks, anti-beauty quarks, the things Leon discovered back in 1977. Those are harder to detect, but I'm expecting there's going to be a breakthrough here as people get a little smarter in how they're looking for B quarks. So even here, we may have more sensitivity. But you can see an enormous sensitivity getting up to a probability of 1. And that'll happen. We'll get to about 10 inverse femtobarns in a year and a half or so. This is the total luminosity of the machine to date. We're about here now. So we are converging on either ruling out or discovering the Higgs boson in this range, and some hope that we might get a systematic improvement there. So this is, I've got a few minutes left. I should tell you that the masses of the particles, like the electron, the top quark, other elementary particles that make up nature, is necessarily also generated by the Higgs boson. So again, we have the same problem. How do we make a massive electron? So a massive electron can sit still. It just moves forward in time and not much in space. We consider what happens if we make it massless. And we'll then, if we set the mass of the electron to 0, then it always moves at the speed of light. And it'll have a spin that is either aligned with the direction of motion, that's a right-handed electron, or it has a spin that's counter-aligned with the direction of motion, that's called a left-handed electron. And as I said, when you turn off the electron mass, these two types of particles are completely independent of one another. Mass unites left and right. So the way the electron actually behaves in nature is it wobbles through space-time, turning left, right, left, right. It marches. And this is due to mass. Mass unites together the left and right-handed electron. However, there's a problem. Again, something Leon discovered. The left-handed electron is different than the right-handed electron. Just like your hands are different. I mean, if your hands were the same under reflection symmetry, they'd look like this. And things under reflection can either be doublets or singlets. In other words, you can have left and right, or you can have something like that. There's no triplet under reflection symmetry. What we discovered, what Leon discovered in the 50s actually, is that if you look at something through the mirror, it will behave differently than looking at it directly. He did this by looking at pion decay. Something called a pi minus decays into a mu minus and an antineutrino. If you look at it through a mirror, this muon could have, for example, spin, be right-handed. I've drawn it right-handed here. It would be left-handed if you look at it in a mirror. And correspondingly, the neutrino will flip its chirality. What Leon discovered is that this is the process that occurs in nature. You always find a right-handed muon, correspondingly a right-handed antineutrino for a pi minus decay. You never see the mirror image. Now, the problem is that the mirror image of a right-handed electron is a left-handed electron. And the left-handed electron has different couplings, different interactions through the gauge principle than the right-handed electron. The left-handed electron interacts with the W. The right-handed does not. That means that when you unite left and right together, you have a charged thing that is then losing its charge and going to a neutral thing, which is then gaining charge, then losing it, then gaining it. The only way that can happen is if the charged left-handed electron dumps its charge in the vacuum and then becomes neutral. Then it absorbs charge back out of the vacuum and becomes charged again. And that thing that carries that charge is the Higgs. So both gauge and fermion masses, all the particles, have to get their masses from the Higgs boson. Whether the Higgs boson is as simple a story as one particular particle that happens to have filled up the vacuum, or it's a more complicated story, that's what we're going to find out. So I think, let me just quickly tell you one possibility. The most popular possibility is something called supersymmetry. Supersymmetry is actually an extension of the number of dimensions of space-time. But the extra dimensions are really weird in that you can only take one step in them. And if you have a particle like an electron, which is a fermion, spin 1/2, if you take a step in that extra dimension, it turns into what's called a boson, spin 0 or spin 1. If supersymmetry were an exact symmetry, we would find for every particle in nature its supersymmetric partner. And we don't, and therefore this symmetry is broken. But we believe it's probably occurring at the weak interaction scale and gives rise to the Higgs. In fact, we get a matching for every boson in nature. There's a fermion. So for the photon, there's something called a photino. For the W, there's something called a wino, the xeno. The Higgs has a partner called the Higgsino. And electron has a partner called selectron, muon, smuon, etc. And we find that there have to be a whole family of Higgs bosons in supersymmetric theories. So the spectrum is really quite rich. By actually measuring this spectrum, we will be able to determine whether supersymmetry is true or ruled out. So I'm going to end here. So what makes this difficult, as I said, is that the symmetry principles define modern physics, and the symmetry principles we can get at first. We understand the gauge symmetry principle. We understand how the weak interactions work, but we do not understand what breaks these symmetries leading to mass. But the overall issue will be resolved in the next 5 to 10 years, and we'll have a new mission. And that new mission will be, what now are the new sets of symmetries? So our new mission statement for particle physics is, find the new symmetries. For example, if it's supersymmetry, what kind of supersymmetry is it? How big is it? Etc. If it's something else, what symmetry principles govern that something else? It might be a new interaction involving new gauge fields. Find the symmetries and discover what breaks them. So that's where we are now, and that's physics in a nutshell. Two and a half questions.
So if your one graph where it had 2009 and then 2011, and you said we're looking forward to the future because there's a certain area of the graph that you wanted to test, what's holding you back from testing that now?
Well, what happens at the tevatron is a quark inside of a proton. Here's a proton. Let's take an up quark. And here's an antiproton. We're accelerating the antiparticle of the proton. We're making them collide. And what happens is you get a anti-down here, just going backward in time. That makes some of W. The W radiates a Higgs. And here you get a recoil W. And that W will make, let's say, a muon and an invisible neutrino. If the Higgs is light, very light, it will decay into Leon's beauty quarks, B bar. So that's the mode Higgs goes to B bar. And these quarks will be associated with jets of particles. And you got to dig inside those jets to make sure there was a B quark in there. There are techniques for doing that. But the problem is there's lots of things at the tevatron that make jets. And therefore, there's a lot of background to this. That happens, this is the dominant thing if the Higgs has a mass of order 140 GeV. Once it gets a little heavier, a new decay mode turns on. And that new decay mode is W, Z, and even still higher masses, ZZ. And this gives me a muon. And this gives me maybe a mu pair or some jets. But the point is, muons are really easy to spot. And they're really easy to reconstruct. And there's little background to them. So as soon as you start seeing mu pairs or lepton pairs in excess, you have mapped out, oh, where was it? Back here. You're in this region, in the central region there. And therefore, your sensitivity has gone way up. You've actually made fewer Higgs bosons here than you would have here. But there's no background. It lights up. And that's where we are right now. And you can see very soon we'll have this, really map this region out. Now, what's rather tragic, I think, is that the LHC will have a very hard time ever seeing this mode. if the Higgs actually weighs 140, you see how low the sensitivity is for us. But we have better sensitivity than the LHC will have to that mode. And you could imagine turning off the Tevatron, let's say in the year 2010, right in here, and let's say the Higgs is here. We will never then see this dominant decay mode of the Higgs, because the LHC can't do it. The LHC just has too much background. The LHC actually sees a different mode, which is a Higgs decaying to a pair of gamma rays. And they should be able to do that in about 5 years at 140 JeV. But in order to prove that the Higgs gives mass to the fermions, the B quark is the heaviest thing it can decay to in that mass range. Top is too heavy, it can't decay into it. In order to prove that, we want to see that mode. So humans could make a really bad decision if they turn off the Tevatron and LHC proves the Higgs is light, and we got to wait around forever until we can build the next machine that could actually see the Higgs to BB bar, like a linear electron collider or something. Anyway, but you know, such things happen. Got me all. Okay, good. Thank you.